Vector machines. Another very important and very fun topic. It has the distinguishing feature that it is the most mathematical of all the topics that we're going to cover. Okay, so if you love math, you're in luck. If you hate math, you're out of luck. But I will try to make it as painless for you as possible. And in particular, it's going to be the first time that we meet constrained optimization. So we've met combinatorial optimization for things like greedy search and beam search tool and decision trees and sets of rules. We've met, of course, gradient descent, meaning continuous optimization. But support vector machines are what really brought constrained optimization into machine learning. And we're going to see how that comes about. Okay? So support vector machines have a bad reputation in machine learning as being impossible to understand. In fact, Andrew Ng has this course on Coursera about machine learning, and he did this heat map about where students, like in Coursera, you do the thing, and then you watch the video, and then you do a little quiz, right? And you can't watch the next video until you get the quiz right? And he did a heat map of where, along the syllabus, people make the most errors. Okay? And I remember him giving a talk about this, and there was like this big pile of red in one place, and I knew what it was. It was support vector machines. So a lot of people have given up on understanding support vector machines, and they just treat them as a black box. Even, however, if you're not going to mess with the insides of the support vector machine, which you don't have to, and again, for example, in your homework, you don't have to. I think it's still very important to understand what the support vector machine is doing, because otherwise you don't know how to play with it and how to make, on how to succeed with it. And I think a lot of the problem is that people have tended to present support vector machines in a way that is actually the opposite of the easiest one. So the way I'm going to present support vector machines here is different from what you will see in I think all the textbooks that I've seen, including Duda, Hart, and Stark. Mitchell doesn't cover this. It is described in my book, The Master Algorithm. And I think once we've seen this, what you have on the slides, even though the slides are sparse, is actually enough, to get to where we want. Okay, so let's, with that preamble, you must be wondering just what are these support vector machines now? Well, the whole thing is that a support vector machine is the simplest thing in the world. Actually, support vector machines are just a type of instance-based learning. Remember the simplest learning algorithm that we ever saw was nearest neighbor? Support vector machines are actually a fancier cousin of nearest neighbor. In fact, Yann LeCun, one of the leaders of deep learning, is notorious for saying that, support vector machines are just glorified template matches because, they're like nearest neighbor, and yet they're very powerful. So, what is a support vector machine? Right? Let's first, you'd be amazed, when you see a book about support vector machines, how long they take to actually tell you just what it is. Right? You first have 5 chapters of math, and then finally you find out what a support vector machine is. I think this is partly because of where it came from. Some people love theory for its own sake, but hey, these are very useful algorithms. So, a support vector machine is just 3 simple things. It's a subset. It's a subset of the training examples, which we call the support vectors. Why? Because examples are vectors, and these are the examples that support the frontier. Meaning, if I took out any one of those examples, the frontier would move, it would fall. So these are the support vectors. So the first part of a support vector machine is just a subset of the training examples. Very simple. Again, that's why it's instance-based learning. It remembers some of the examples, then it uses them. The second one, again, very natural, is a vector of weights for them. Just like, say, boosting, right? Each example is going to have a weight. Completely trivial. And finally, another thing that, is not new, but, it's very important, is the similarity function. It's a function that you give it 2 examples, and it returns a non-negative number saying how similar they are. Okay? The higher the value, the more similar they are. Okay? All right? So this is called the kernel. Okay? This comes from math, but really just think of it as a similarity function. To be very technical, a kernel, as we'll see, is a similarity function with some special properties, but just think of it as a similarity function. Right? It's like I give you 2 examples, and I want you to tell me how similar they are. That's what the kernel is for. Okay? So as you see, nothing new here, right? Just instance-based learning with weights on the instances, which again we've met before, right? It was the weighted, nearest neighbor algorithm. And then so let me just finish. So given these 3 pieces, what does the support vector machine do? Very simple. When you see a new example, here's my good old friend XQ, the query. What I do is, and by the way, for support vector machines, it's convenient to assume that the classes are +1 and -1. Okay, not 1 and 0. Right? So the class is going to be +1 or -1. So what is the class that I predict for an example? Very simple. It's just going to be the weighted average of the classes of the support vectors, where the weight of a particular support vector is its weight times the kernel. Which again is very intuitive. It just means that support vectors that are more similar to the query have more weight because they're closer, right? Now, of course, the math is going to be interesting, but the intuition is just the same as in nearest neighbor. Okay, so I do that weighted average. I take the sign, and the sign is the class. Okay, so if on balance I have more examples with higher weight and higher kernel values predicting positive, I say that the example is positive. Otherwise, I say that it's negative. Sorry, somebody here had a question?
Yeah. So those weights are only for subset for support vectors.
Well, actually, one way to think about this is that like all the examples have a weight, but most of them are going to end up with a weight of 0, so I can just throw them out.
Oh.
Okay?
I don't see how that's the average. Right?
Well, it's not a weighted average in the sense that it's not a normalized average, but it doesn't matter because I only care about the sign.
Okay.
Right? I didn't normalize you.
Okay.
Right? But here's, you can think of it as voting. Maybe a better way to think of it as voting is like, I'm going to have votes for the class +1, and I'm going to have votes for the class -1. An example's vote for its class is its weight times its kernel. So the higher the weight an example has, the more it counts, naturally. The more similar the example is to the query, the more it counts, which is also natural. Okay? So a small number of close examples could be offset by a larger number of farther away examples, and so on. Yeah.
I was wondering, what would you do if you have some like garbage on the boundary and it will affect? I mean, since it's important what's on the boundary, what if you have garbage there or something?
Yeah. So for the moment, we're not going to deal with garbage, for which the technical term is noise. Right. So support vector machines actually, when they were first defined, were actually just for noise-free data, just like the perceptron. Again, you can think of like the genealogy of the support vector machines actually goes all the way back to the 60s in the perceptron. But then like one extension was multi-layer perceptrons, and support vector machines are a different extension. And in fact, the history of this is kind of amusing because Vapnik is a theoretical statistician. He never worried about algorithms for most, and he did this work in the 60s and 70s with Chervonenkis. And he was happy doing theory. This was in the Soviet Union, and then one day the Soviet Union collapsed, and life was not good, so he immigrated to the United States, went to work for Bell Labs, the famous Bell Labs. And there his colleagues started saying like, when you're going to turn this into a useful algorithm? And then he finally, after 30 years, got to thinking about it, and guess what? Support vector machines came out. Right? So support vector machines are a peace dividend. Right? If the Cold War hadn't ended, we wouldn't have support vector machines because Vapnik would still be doing pure math in the Soviet Union. So there you go. This is how things work in the real world. I'm glad that this happened, right? Because we really wouldn't have support vector machines. Okay, so questions? But now I just told you that support vector machines are just a type of instance-based learning. The way they are usually presented, as I already hinted, is as a generalization of the perceptron. Okay, so you hopefully are getting some cognitive dissonance at this point because nearest neighbor and perceptron, right? Those are totally different things, aren't they? How could support vector machines be a generalization of both? Which actually, raises the question, what exactly is the relationship between perceptrons and instance-based learning? Anybody care to hazard a guess? Actually, let me give you a hint. The perceptron, the one-layer perceptron, is a special case of nearest neighbor. It's a special case that you get when you pick a particular similarity function. And it must be an awful similarity function because that whole power of nearest neighbor to form very complicated frontiers disappears, and all you have is a hyperplane. So my question to you is, what is the similarity function that when you plug that into nearest neighbor, it becomes the perceptron algorithm? And to make this even spicier, I'll tell you, the similarity function. You've known it for a long time. It's going to be nothing new.
Is it like clustering?
Well, what's the similarity function that you use in the cluster?
Must be some Boolean function.
Somewhat?
Boolean.
No, not Boolean.
You find like a set of math.
No. These are all very, well, again, finding the center of mass is not a similarity function. A similarity function is like I give you two examples and it returns a number.
Just adding how many?
You draw a line between
adding
center of mass.
things, one
Chop them.
Well, Euclidean distance is adding a bunch of things. Hamming distance is adding a bunch of things. So clearly that, I mean, maybe you're true in general, but that is far too vague, right? Because it includes obviously measures that aren't the right one. More suggestions?
Distance from line.
Weights.
Meaning what? Again, I want a function that I give to you two vectors, right? Like, I mean, Euclidean distance is such a function, right? I give you two vectors and it returns a non-negative number. Hamming distance, I give you two bit vectors, it returns a non-negative number. And what is another function that you know very well, that when you plug it into nearest neighbor, it produces the perceptron algorithm?
Inner product.
Inner product. Who said inner product? Congratulations, you hit the jackpot. But why is it the inner product? Prove to me that you weren't just lucky. What is your VC dimension?
I mean, because inner product can represent distance, and I mean, in perceptron you have inner product, which is like when you have weight multiply. You can think of a weight inner product with array of inputs is an inner product when you look at.
Yeah. Exactly right. So notice the steps in this, right? We're going to see the proof shortly, right? Which is a little bit more than this, but you got exactly right. First of all, the inner product is a valid distance measure, right? Of course it is, right? And number two, this is what the perceptron algorithm is doing all the time, is inner products. So somehow that's got to be involved, right? At the end of the day, when you're doing your inner product of your weight vector, right, with the new example, what you're really doing under the hood is you're doing a dot product of the query example with every example that went into learning that weight vector. And now, of course, if that's all that's happening, then you do just get a linear boundary because it just reduces to a dot product between the weight vector and the example. But now let me prove that last claim, which is the key step. Is like, why is it that doing the dot product with the weight vector is the same thing as doing the dot product with each of the training examples, right? Because otherwise it's not nearest neighbor, right? Near neighbor is you compute the distance to every example, and that's how you find the class. Okay?
Is there a difference between inner product and dot product?
No, for our purposes, it's the same.
Okay.
Yeah, it depends on what branch of science you have come from. Okay. And what just to make sure that we're on the same page, right? What I'm talking about is like you have two vectors and you multiply, right, the corresponding positions and you add up the results. Okay. It's like, remember. What is it perceptron does? It computes the dot product or inner product between the weight vector and the example. Right? In the same way that you do that, you could do the dot product between two examples. Okay, so everybody would know how to do that if they needed to implement it tomorrow. Right? You won't, but but there you go. So let's see why this is the case, right? You have the general chain of reasoning, but now let's see the proof, which is very simple. So here is my what is called discriminant function, right, for the perceptron, right? The class that I predict for the query example is the sign of the sum, right, over all features of the weight of the feature times the value of the feature in the query example. Do you agree? This is the definition of a perceptron, right? This is the function that it has learned. Agree? But now let's look at how it learns this function. Remember what the perceptron does is that if the example that it sees is correctly classified, what does it do? Nothing, right? Another useful word in machine learning, nothing. Okay, it does nothing. If it is incorrectly classified, right, what does it do, right? What it's actually going to do is, like, remember, it's going to multiply the difference between the training, the target value and the output value, right? But notice, that difference can only be three things: 0, +2, and -2, right? Therefore, it's always a constant times the value of the feature times the learning rate. Therefore, it's always a constant times the value of the feature. So at the end of the day, when you squint closely at the perceptron algorithm, all that happens is that when you get an example wrong, you add a multiple of that example to your weight vector. Which means that at the end of the day, the weight vector is just a weighted sum of the examples. If an example was always correctly classified, it will be 0. But in general, it'll have a weight that's a function of the times that it came up wrong, and and the learning rate, and the value of the feature there. Okay. So second step, the weight vector is just a weighted sum of the examples times, of course, the respective classes. Right. Remember, this also again it's a constant, but it's plus or minus 1 depending on what the class was. Okay. So everybody happy with these two steps?
This is the predicted class, right? Not the
Yeah.
actual class.
No, the predicted class, right? We're trying to see how the perceptron computes the predicted class, given how the weights were learned. Okay, so this is how it computes the predicted class, using these weights, and this is how these weights were learned. Okay, okay. Now we just have to combine these two things, right? So here's a fairly straightforward piece of math. So the predicted class, right, is going to be the sign of this function, right? And now I'm taking this expression and I'm going to plug it in there. Right? It used, the sum over all the weights, so the weight times the feature, right? So here's the weight. I have an expression for the weight, so I'm going to plug it in. So far, so good. Therefore, I get this expression in here, right? This expression is just this expression with this expression plugged in. So far, so good. Right? Here it is, right? Happy. Okay, and now I'm doing a sum over j. Remember, j is the features, right? This runs over the dimensions of the space. And I is the examples, right? I'm summing over the examples, right? Remember, summing over the training examples. But addition is commutative, right? So I can switch the order of these. Okay? And this guy is the same for everybody, so I can put it in there. So what I get is I get on the outside the sum over I, right? Times the alpha I times the class times inside, guess what? The sum over j of xq times xi, namely their dot product. Okay? Well, this is a really simple piece of math, right? There's really two steps to this. Like, the first step is replace this expression, oops. The first step is just replace this expression into this expression here, and the second one is just apply the distributive law. The distributive law here and the commutative law of addition here. Okay? Simple math. Okay? So what I get is indeed that so now, like, here's the punchline. We just concluded that this is the function that the perceptron is computing, and guess what? This function has exactly the same form as this function that we saw here, right? Except that for kernel, I'm using the dot product, right? If for kernel I use xq dot xi, then I get this expression here. Okay? Everybody agree?
It's going to sound dumb, but when you did the commutative rule, we were summing over j features and I examples, but now we've dropped j.
No, well, because the j is inside the dot product. Remember, the dot product is sum over j of xij, xqj. Right? So the sum over j is actually now hidden in the expression of the dot product.
Okay.
The expression of the dot product is just a shorthand for this longer-winded thing with the sum. Right? We don't want to be carrying that sum thing around. That's all. Yeah. Okay? Very good. So, here's another view of it. Yeah.
So earlier by definition, the y's come from the subset of training examples, right?
No, so they are the y's of all the training examples. Some of them will wind up with a weight of 0, and I can ignore them, but every example has a weight which could be 0.
But how we define that subset? How we choose it?
Well, I haven't told you yet. In a way, you can look at the support vector machine as a very mathematically sophisticated way to pick the relevant examples and their weights using constrained optimization. We looked at things like, the distance weighted nearest neighbor. And remember the edited nearest neighbor algorithm where we throw away some of the examples? It was purely heuristic. Right? It was a greedy search and there was no guarantees. What's going to happen with the support vector machine is that we solve the same problem, but we actually have a convex optimization problem that we can guarantee was solved optimally. So it's a nice thing to have. And remember, people have been doing research on nearest neighbor for 30 years before Vapnik came out with this. So there you go. There could be even bigger ideas waiting to be discovered right now. And you could think of one on your way home today. And remember, if you do that, the first thing to do is to tell me. After which you will have only a few minutes left to live, but you will have, you will have a place, an unknown place in history, but nevertheless a place in history. So here's another way to look at SVMs, which is the way they are usually presented. But I think at this point it'll be much easier to kind of like to grok all this. Step one, take the perceptron. Okay, take your good old-fashioned perceptron. And you can look at the perceptron and say, like, the problem with the perceptron is that it uses a stupid distance function. Why does it use dot product? Let's use something a little bit more intelligent. Okay? So we're going to replace the dot product with an arbitrary similarity function. Big step. Okay? At which point, all those perceptron convergence theorems, well, that no longer applies, but we're going to find something better. We now have, obviously, a much more powerful learner, because as we just saw, right, this learner is a form of k-nearest neighbor, right, as a result of which it can learn any function given enough data, as the corresponding theorem shows, right, so much more powerful, okay? And now, here's a very important concept in support vector machines. It's the concept of the kernel matrix. Support vector machines are all about the kernel matrix, also known as the Gram matrix. But let's keep calling it kernel matrix. The kernel matrix is the ijth entry in the kernel matrix Kij is the kernel between the ith and the jth examples. Okay? And in the same way that some of the elements that we saw, all they needed was the sufficient statistics, right? And then we could throw away the data. In the support vector machines, all I need from the data is the kernel matrix. Okay? I need to know the dot product, or generally the similarity function, the kernel between any pair of examples. If I can compute that, I'm good. Okay. And now here's something that I will not prove, but actually, and the details of this are actually not example, but not important. But let me just state it. If my kernel matrix, first of all, is symmetric, and distance measures are usually symmetric, right? Because it's distance between A and B is the same as distance between B and A is one of the properties of a metric, and usually we use metrics for distance functions. So let's say the matrix is symmetric, and in addition, it's positive semi-definite, right? How many people here know what positive semi-definite means?
I used to.
Okay, good. So 2.5. Fine. But so here's the good news. Actually, it's not going to matter, right? It appears in all the theorems, but actually then somebody later showed that even if it's not positive semi-definite, you can actually have, essentially all the same theorems with basically looser bounds, okay? So positive semi-definite just means, or an equivalent statement to make is that all the eigenvalues are non-negative, right? And I know that everybody here loved eigenvalues when they learned it in linear algebra and understood them very well and remember exactly what they mean, right? In case you don't, then never mind, right? Just ignore this technical condition as they call them. What is the point here? Is that if I have a kernel, and by the way, this is also why people often call this a kernel as opposed to a similarity function, is that similarity function not imposing anything on it. Often, to call something a kernel, it has to satisfy this property. Okay? But for now, we're just talking about the kernel matrix, which is a simpler object, and it suffices for our purposes. Here's the amazing property, is that if the kernel matrix is symmetric and positive semi-definite, so symmetric and positive semi-definite, then that kernel is still a dot product. We've only been doing dot products all along, except it's in a transformed space. It's not a dot product in the original space. Well, it's not, right? Look at the expression. It's not the same as dot product. But what I'm saying is that I can define a derived space, typically much higher dimensional. And in this derived space, I'm still only doing the dot product. And the beauty of this is, I can now do nonlinear classification using only linear algebra. I mean, the beauty of this for a theoretician is beyond words, right? It means that you can do all your theory and actually have something that is powerful in practice. Right? This is often called the kernel trick. The kernel trick is, and it's used, since SVMs, it's been used way beyond, SVMs. It's been used for clustering, for dimensional reduction, for all sorts of problems in machine learning. And the thing is always the same, is like, I took an algorithm, and next week we'll see, for example, principal components analysis. It's an algorithm for dimensional reduction. All it's doing is dot products. Remember, a matrix vector multiplication is a bunch of dot products. And we can go to all those dot products and replace them by a kernel, computation. And now suddenly everything that was linear is now nonlinear. Right? You get the same kind of gain that we did going from the one layer perceptron to the multi-layer perceptron, meaning we go from something that's very restricted to something that is infinitely powerful, meaning that you can learn anything. All because of the kernel trick. And as a huge bonus, the weight learning problem that we are now going to solve is actually going to be convex. Which, if you contrast with the mess that learning a multi-layer perceptron is, this one will make not theoreticians, but applied data scientists weep for joy. Because all those hours they used to spend, tweaking parameters, trying to escape local optimum, or trying one thing or another, and then I get one result, you get another result, and then next week you get a different result because they all went to different local optima depending on where you started. With support-type machines, that doesn't happen anymore. I define my convex optimization problem, right? There's only one optimum. There are no local optima. No matter who does the optimization using one algorithm, as long as the optimization works, it will return the same result. And this is as much the reason SVMs took off as the fact that they were accurate. In fact, when SVMs first started to become popular was when, Vapnik, who was actually, Jan LeCun was also at Bell Labs at the same time. And Jan LeCun and his friends has spent years developing, multi-layer perceptrons, and in particular, convolutional neural networks that were engineered for the problem of digit recognition. Jan and Vapnik and co. came along, and they solved the same problem equally well. It wasn't that they were more accurate. It's that using support vector machines, they got equally good solutions with no tweaking and no years of, defining something for the problem. Which, for you as a data scientist, that makes a big difference. It means I'm going to take one day to do this instead of 6 months. And then in a bunch of problems, they got better results and whatnot. And again, these days on a lot of problems, they still are the best approach. It's not deep learning. Okay? But now, you're saying, this is all very nice, but, this is a really strange idea. How come? Right? Here's the formal statement. I'm saying that the kernel between x and x prime can be expressed as phi of x dot product phi of x prime. Okay? It's a dot product between two vectors, except these vectors are not the original vectors. They're derived vectors. If the vectors were the original vectors, then this would just be the ordinary dot product. Okay? So I'm not going to give you a proof of this. It's, slightly beyond the scope of this class, but I will give you an example that I think will make it very intuitive why this is the case and why you get so much power out of SVMs. So what are some of the, before I can give you the example, let's see what are some of the kernels that people use. Right? By the way, designing kernels is something that you could, like every machine learning method has a place where the black art goes, right? And yes, SVMs have a lot of less black art than neural networks, but there's still one place where the black art goes, and that's choosing the kernel, right? When you see this competition, often between people in the same lab or the same company, one say like, no, we're going to solve this with SVMs. And the other ones are like, no, we're going to solve this with deep learning. The deep learning people are tweaking the architecture, right? And all those parameters that we talked about. The SVM people are spending 90% of their time trying different kernels, okay? Having said that, it's just like nearest neighbor, right? Your similarity function could be arbitrarily fancy, but the basic ones often work very well. And there are, the three most basic ones are what's called the linear kernel is just a dot product, okay? And actually, this linear kernel, surprisingly, is actually useful for a lot of things. So for example, for test classification, what people usually use is the linear kernel. And at the time that people, brought, SVMs to text classification, the dominant algorithm was, guess what it was? It was naive Bayes. Naive Bayes at one point did better text classification than everybody. Than decision trees, than multi-layer perceptrons, than nearest neighbor. But the problem is that when you're in very high dimensions, like 10,000 words, even naive Bayes can start to overfit. There's a little word that by accident only happens in class A and never in class B. Well, this is a perfect discriminant between class A and class B. In that case, just the linear kernel can be enough to make, so with a linear kernel, the SVM is still a linear classifier, but it overfits less than naive Bayes because of the VC dimension guarantees that we're going to see. Okay? But of course, things get more interesting when you have nonlinear kernels. A simple nonlinear kernel, the one that we're going to use as an example, is the polynomial kernel, or polynomial kernels in general. So polynomial kernel, as the name implies, is where the kernel is a polynomial function. And the simplest and most popular type of polynomial kernel is you just take the dot product and you raise it to some power. Okay? As a result of which, you agree, it is now a nonlinear function. Okay? So in the same way that we need a nonlinear function in neural networks, or maybe in a different way, but in a solid analog, we're going to need nonlinear functions here in order to do something more powerful than just hyperplanes. Okay? The third one, and in fact, probably the single most widely used type of kernel is the Gaussian kernel. The Gaussian kernel, as the name implies, is just a Gaussian function. Not normalized, because we don't care about the normalization, right? This isn't a probability distribution, but it's what? It's the bell curve applied to the distance, right? So as the distance between the examples increases, at first the kernel goes down slowly, and then quickly, and then slowly again, like a bell curve. Okay? This is what exponentiating minus blah blah is doing. Okay? This is the exponential of minus the square of right, etc. Okay? So this is the Gaussian kernel, and the theory is a little bit more complicated for Gaussian kernels, but nevertheless, well, the first thing that you have to prove is that these things are kernels, right? And it's actually a few lines of math to show that this is a kernel. It's not obvious that it's a kernel, but it is, and it's a very popular one. Okay? And it's the kernel that most captures this notion that this is just another form of similarity-based learning, right? It's basically just taking the distance, which is a function that's kind of like an inverse of a similarity, and turning it into a similarity by doing e to the minus it. And this sigma is actually an important parameter, right? It's the variance of the Gaussian, and it determines whether your kernel falls off very quickly with distance or very slowly. And SVMs are only going to have a couple of parameters to tweak, as opposed to neural networks, which have arbitrary large numbers. But this is going to be one of them. If you're using a Gaussian kernel, which there's a good chance you will. Yeah.
How does it scale with data? It seems like a lot of computation needs.
Yep, not very well. This is in fact the Achilles heel of support vector machines in the modern age, is that they do not scale to big data as well as deep learning does, because of, guess what, the kernel matrix. Right? The kernel matrix is quadratic in the size of the data. Now there are all sorts of things. I mean, there are papers and papers on how to scale up support vector machines, changing this and that to make it not be quadratic. But at the end of the day, it's still not as easy or as scalable as something like deep learning.
So it looks like that if we have a high dimensional space, but then I don't have quite enough data, then this is probably the
No, actually, the high dimension per se is not a problem. Because remember, I need to computing my kernel matrix is actually only linear in the dimension. Right?
So high dimensional is good.
Yeah.
Like when I have a problem where I have a lot of features but not that much of data, then this works too.
Yes, SVMs are a very good choice for that case. In part because you can see what SVMs do as fighting the curse of dimensionality better than your neighbor does. Now, sometimes you see the claim flying around that SVMs solve the curse of dimensionality, and you know at this point to be suspicious of that. SVMs actually, and we'll see why that, because there are some bounds for the generalization accuracy of SVMs that do not depend on the dimensionality. But just because they don't depend explicitly doesn't mean that they don't depend implicitly. In fact, they do implicitly depend. So yes, SVMs fight the curse of dimensionality a lot better than nearest neighbor, but they do not, at the end of the day, they still suffer from it. Because nobody, there is no ultimate solution to that problem. Okay, but now why? So let's, here's the example that I promised, which I think is kind of like going to make this all, beautifully clear. Let's suppose that we're going to use a polynomial kernel, okay? And let's suppose that I have two vectors, u, which is u1, u2, and v, which is v1, v2, okay? And now I'm going to compute the quadratic kernel between these two vectors, right? So this is the polynomial kernel with d, just equal to 2, right? It's the simplest useful thing that you can do, okay? So let's, and you remember my claim was that this is true. So the kernel is equal to a product, the kernel between two vectors is equal to the dot product of a vector, of a phi vector that's just a function of the first vector times another one, or feature vector. That's what we usually call it, although features is a bit of an overloaded term, but think of like the original example on the derived feature vector, right? And the claim is that the kernel can be expressed as just a dot product of a feature vector on the first example times a feature vector on the second example. Okay? So let's see why that is the case, for this simple example. Let's just do it, right? So u dot product v squared. What is it? Well, u dot product v is u1 v1 plus u2 v2, right? By definition of dot product. Everybody agree? And now let's just square it. There's absolutely nothing complicated going on here. Well, what do I get? I get u1 v1 squared, right? Meaning u1 squared v1 squared, right? You agree, right? It's the square. This is a plus b squared, right? A plus b squared is, sorry to bore you with this, it's a squared plus b squared plus 2ab. Everybody agree? So what is a squared? It's u1 squared v1 squared. Okay? What is b squared? It's u2 squared v2 squared. And what is 2ab? It's 2u1 v1 u2 v2. Right? This is just, applying the square. Okay? But now, remember, our challenge is to turn this expression that we have at this point into this expression. Okay? At which point we have proved that this kernel is a dot product in the derived feature space. So far, so good? Well, how can we do that? Actually, it's not that hard. Look, I want this to be a dot product between two vectors, one of which only depends on u, and one of which only depends on v. Well, clearly, the first component should just be the squares, right? Well, here's u1 squared is going to be the first component. The second one, the same component for the second vector is v1 squared, right? You agree? When I do the dot product, these two guys get multiplied. Well, here they are. So far, so good? Right? The second one is just going to be the second component squared, right? So here it is, right? So u2 squared and v2 squared. Okay, so far, all that I've done is I define my derived components by squaring the original components. Okay? Nothing difficult. I'm allowed to do that, right? I can square the components. But then finally, the third one, I had here 2u1 v1, u2 v2, right? How can I split this into something that's just a function of u and something just a function of v? Well, easy. The first, the u part is going to be square root of 2 u1, u2, right? Because these are the factors here that come from u, right? And the gun over there is square root of 2 v1, v2 because these are ones that depend on v1 and v2. Why the square root of 2? Yeah, it has to be the same for both, right? Because it's the same kernel function, but when you multiply the 2, I have to get 2, therefore it has to be square root of 2. Okay? So what I've proved is that this is indeed of this form. What I did was, here's the recipe. You give me an example, u1, u2, and I turn that into the example u1 squared, u2 squared, square root of 2 u1, u2. Same thing for v, same thing for anybody else. I have changed the representation of my example, right? And what I've shown is that applying the polynomial kernel is just the same thing as applying the dot product in this derived space. Okay? Why is this so powerful? Because notice, suppose that the dividing line was a quadratic line, right? Suppose that the frontier between positive and negative was a parabola or a circle, or actually, maybe this is the most visualizable case, is an ellipse, right? If my data, or actually let's just take a circle, which is actually the simplest case and the one that works with this example, right? Right? My positive examples are inside, my negative examples are outside. With a linear frontier, I can't represent that, right? It's a circle. But guess what? With a quadratic frontier, now I can. This nonlinear frontier on the original, u1, u2 plane, when I add that third dimension, and square the other two, actually now have a space in which this circle has become a linear frontier. So the key trick in the support vector machine is that a nonlinear frontier is a linear frontier in some space. And what I have to do is find that space, and then life is good. Then all I have is a plain old perceptron. Or a plain old perceptron will solve my problem. Okay? So it's very powerful. And of course, this is a toy example with quadratic, with the quadratic boundary and a quadratic kernel, but in general, you could have, it's like near snap, you could have an arbitrarily complex frontier, and the SVM will be able to learn it. And we will have generalization guarantees.
And then because it's a convex optimization,
It's much easier. Why is it a convex optimization? Because it is like doing gradient descent on the perceptron, right? Because in this space, the frontier is linear. Sorry, the function is linear. Therefore, the objective function, right, is going to be quadratic. If it's something like this, we'll see what it is, but it's going to be quadratic. Therefore, the function they're optimizing here, instead of being this incredibly capricious thing that is on a multi-perceptron, is just a high dimension parabola. Question?
So your kernel function has to be decomposable like this. You can't pick any arbitrary kernel function.
Well, yes, exactly right. But remember, the conditions that I need for that to be the case are actually, very reasonable. It's just that the matrix has to be symmetric and positive semi-definite. Nothing else. And as I said, even if you like those conditions, there are theorems that show for any similarity function, but then the math is different. So when somebody develops a new kernel, the first thing they have to do is prove that it is indeed a kernel. In some cases, that proof is actually not trivial. But then once it is a kernel, then suddenly you have all this machinery working for you.
You explain what is positive semi-definite?
Yeah, so positive semi-definite, is equivalent to saying that the matrix has no negative eigenvalues. So a practical way to do this would be, I give you the matrix, you do an eigenvalue decomposition for which you can use any good old-fashioned linear algebra package, and if all the eigenvectors have positive eigenvalues, then you're good. I mean, what is this really saying geometrically? It's saying that the curvature is the same in all directions. It's saying that you don't have saddle points and exactly the things that would lead to complications. Okay.
So that's why you don't have local minimum, because you have a...
Yes. Again, I'm kind of abstracting over a lot of details, but I think this is a reasonable intuition. Yeah. More questions?
So initially you were asking the question, if we have infinite number of points, how can we represent it with hypothesis with one argument?
Yes, but that is the polar opposite from what we're doing here. What we're going to do here is we're going to have, so an SVM, right? Now we know what an SVM is. If you give me infinite examples, I could not an infinitely large SVM, and yet it could have a finite VC dimension for reasons that we have yet to see.
Mm-hmm.
Yeah, so we haven't actually gotten to the relevant part yet, but we're making our way there.
But solution for that is not this kernel trick yet, where you increase dimension.
Well, no, what's going to happen is that I'm going to have, actually, let's just defer this until because we're kind of spinning our wheels until we get to that part. Yeah.
Yeah.
But if you're not happy, then just ask me the question again. More questions? Okay, I think this is a good place to take a break. Here's what we're going to do after the break. As usual, we now know, so the first thing we did was we studied the representation. Right? Now we know what an SVM is, but now the next question was all about how do we learn it. And here's the answer in 3 parts. Well, there's 3 things. Remember, there's the kernel, there's the examples, and there's the weights. Right? So, how do you choose the kernel? Black art. I mean, there's a lot of literature on, deriving kernels and blah-da-dee-blah-da-da, and the true answer is black art. Right? This is all, or another way to look at this is like, this is where your talent, right? This is where you earn your $1 million salary as a data scientist. Not just this, but one place. So I'm not going to say how to choose the kernel here. It's something that when you are applying SVMs to a problem, you have to try different kernels and so on. How do you choose the examples, right? Remember, the support vectors are a subset of the examples. And the beautiful answer here, right, in your scenario, this was a difficult question here, is like, this is going to be a side effect of choosing the weights. The way we learn SVMs naturally causes a lot of the weights, hopefully the great majority of the weights, to be 0. It just falls out of the optimization that most of the weights are 0, as a result of which you can throw away the corresponding examples. So you do not need to explicitly have a way to choose the examples. It falls out of the weight optimization. And finally, here's the key question around which, this is what an SVM learner is like, how do you choose the weights? And the way you do it is by doing something called maximizing the margin, and after the break we'll see what that means. But this is the next so the first big idea that we met in SVMs was kernels. The next big idea is maximizing the margin. And this is all still for noise-free data, and then when we try to do it with noisy data, then we're going to have a third big idea, which is slack variables. So really the 3 key ideas in SVMs are kernels, maximizing the margin, and slack variables. We've seen kernels. The next thing we'll see after the break is maximizing the margin. Okay? And it's 7:55, so let's restart again at 8:05. No, that won't necessarily give you good estimates. Right? So what you want to do is like you want your classified to output probability. So you either want to use a classifier that outputs probabilities, or you want to retrofit probabilities onto the output of your classifier.
Outputting probabilities is one thing. Let's say 0.8 probability
Well, it's like for example, if I say this is of class positive with probability 0.7, that's my So for example, for SVMs, SVMs don't output probabilities, but there's something called Platt scaling, and then after John Platt that invented it, that actually turns the output of the SVM into a well-calibrated probability that you can use to measure the probabilities.
Yeah, so I'm not talking about, so let's say my problem requires me to output a classification, which is a probability that was calibrated or not. And then it also asks me how confident is your classifier.
Oh, in the probability?
In the probability.
Oh, for that you have to use Bayesian methods, right? Because you need the distribution over the probability, which means you're doing now Bayesian methods.
So I read somewhere Bayesian
Yeah.
distribution.
Yeah, exactly. For any method, there's a Bayesian version that will output, a probability distribution over the service.
It wasn't safe to use 5 probabilities. And then she dropped that. She used the split.
Yeah, project 3 and project 4 had different splits. That was my question.
Yeah, that's a different thing.
If you use the original data, you can upload variance because you are producing one output per class, per test data.
But how are you you have a sample, you have a value split. How are you computing variance?
So I'm taking the same.
Why don't you use the bootstrap into the 5-fold?
You can. Then you are saying that for each 5-fold, you are
Yes.
going to.
For each 5-fold, you
10
get
bootstraps.
the divide by 5. You get the first fold, that's your test data. You train, you get 10 different bootstraps for the 4
For
folds.
each fold.
For
It's
the
too
4?
much.
What?
Isn't it?
No. Alright.
Huh? Because for each, you need to now do 30 bootstraps, right? 30 is what she asked.
I run very well.
That would take like a
I
second.
don't understand the
It's
bias or variance key definition.
Yeah, it's not true.
So that's what I basically divide it by 5. Then I get like the first 4, that's my test
I
data.
will people with
Then I get the 4, I get 4 like 10 different bootstraps, so 30 different bootstraps using bagging on that, 20 different.
Well, bagging and bootstrapping is different. That's what I'm saying. So it's 20 multiplied by 30. So it's 600.
Well, classifiers doesn't matter if it is a one single tree or 50 decision tree. Based on that, we calculate the variance on the type 2
You can do that, but it's like 600 times.
I'm using decision trees, ensembles
So you
of
finally
decision
learn
trees,
a 1-0
and I'm using
by classification.
30 bootstraps as 30.
How will you use
So it's actually more 1500.
now vectorly
I-
vectorly I will make a Java like
How
before
is your bagging
Well, I designed it, so I'm pretty familiar with it.
I didn't want
Oh, what you talking about? Because
Oh, the first
oh, number 1 is regular, the back. Oh, that's the
decision tree.
But stabilizes after.
So my understanding is
You didn't
basically they have
after it was very stagnant.
trees there.
Exactly.
Mine is going down. Take 1, 2, 3, 4, 5.
The configuration I think they do. Because if you have like x1, x2, x2, positive positives, and x1, x2, then negative.
So I think the question you're asking is about the whether these are syntactically different or semantically different.
Because
Right, I could have two trees that are syntactically different and yet are semantically the same in the sense that they make the same functions. And these things in general may be different, but we actually don't, we will accept either answer for the homework. But you are right. I mean, if this is your question, these things are in general different. So the number of syntactically different trees in general can be higher than the number of syntactically different trees. Yeah.
If you have like.
But remember, again, from the point of view of the VC dimension and from the point of view of packed learning, right, what matters, I mean, you've seen this now, right, is like, it really doesn't matter what the hypothesis is syntactically. What matters is what are the frontiers that the hypothesis draws, and therefore what are the frontiers that the set of hypotheses is able to do.
Second question is easier. About variance. So SVM, once you create a measure variance, you never do a variance of a hypothesis. You only do the variance of a class of the classifier. Several different training cases.
Yeah. Remember, what is varying is the training data. The variance and the bias are averages over training sets.
Actually, I tried to be sort of there.
Ideally, you would have different training sets. We use, the bootstraps in order to simulate having more training sets. You have a question?
They also use the
Yeah,
SVM
or picking from the available ones.
But the library still.
Oh yeah, but there are infinite available ones. And often, as with everything, right, you can get better results by designing it. I mean, remember, the kernel is deciding what makes things similar. And this way, it's just like this flavor. It's a really crucial issue. If you have a good kernel for your problem, you'll do well. If you don't, you won't. So it's always, people always start with the generic kernels that you can just pick off the shelf. There are a lot of them, but often it's better that you get the best results by designing it. That incorporates what you know about similarity in that domain.
The test data, it always knows what its scale is, and it would convert the test data to that scale as well. So it's like really, is it matter of fact?
Well, that's usually what people do, right? They start out by trying a bunch of things, and then based on the results of that, they try to figure out, how they could, design an even better kernel.
There's a grid search.
But is there a way that because you can, I don't know,
File, which you can grid search all the parameters.
You can do things like, do kernel algebra, do products and sums of kernels and whatnot, right? But those people do those things, but they don't necessarily guarantee that you will get the best kernel. Right? So there is no choice that you can to try different things and try to understand the problem. So the kernel, this is a network which is normal. The primitive thing here is the kernel function. I can give you any two data points and I get back a value. Based on the kernel function, you can define the kernel matrix of the data.
Over the range of x and x prime.
Not the range, it's just the kernel matrix is just the kernel function applied to every pair of data points.
Okay.
And that is what I'm requiring you to understand the method.
Okay,
In
so
fact, I could have conditions on the function, but they're actually more involved
so it's whether the function is
Otherwise, the prediction is not going to work right.
kernel matrix applies just to the set of examples.
It's positive example.
For the set of examples.
Yes, for set of examples. But what I need to do is to prove that for any set of examples, it will be positive.
I want to use but kernel to be like absolutely new. I recommend you to do more stuff.
Okay, let us continue. So the next crucial notion is maximizing the margin. The two words we will hear most frequently when talking about SVMs are kernel and margin. So what's the idea of the margin? This actually predates the idea of kernel. Back in the late 60s, when Vapnik and Cherenkis were thinking about VC dimension and whatnot, they were thinking about the margin of a perceptron before they were even thinking about kernels and long before there were SVMs. So what's the idea of a margin? It's the following idea. If you think back to how the perception algorithm works, right, what happens is that the frontier keeps moving as I get examples wrong, right? If I get an example wrong, I move the frontier in the direction that brings it closer to being right. And as soon as the frontier lands somewhere that all the examples are on the right side, I stop. Meaning all the positive examples are on one side and the negative examples are on the other side, then I stop. But I could actually have stopped in many different positions. So for example, let's suppose that I have this set of positive examples here and this set of negative examples, and here are two perfectly valid frontiers, both of which could have been returned by the perceptron algorithm. There's the frontier in solid black, which I'm going to put as red. Right, so this is one frontier. Of course, now it's no longer a straight line, but bear with me. Okay? And then there's the dotted line, which I'm going to draw in let's say, blue. Right? And you agree that both of these are valid, right? They both separate the data. Both of those could have been returned by a perceptron. Okay? But now, what is your intuition? If I asked you to pick one of these to be your frontier, would you be indifferent, or would you pick the red or the blue?
Red.
Everyone would pick the red, right? Why is that?
Because when new example comes in, it's a higher chance that if I pick red, higher chance that
Exactly. The intuition is that, like, well, this guy here is really cutting it close. If I'm so close to a negative example in the data, there's a good chance there would have been a negative example not in the data but on the other side. Okay. So what I really want to do is I don't just want to be satisfied with any straight line. I want the straight line that is as far as possible from all the examples. Or to use the technical term, that has the maximum margin to all the examples, where the margin is simply the distance between the example and the line. So for example, the margin for this example and this line is this. And this is a crucial example because it has the smallest margin. On this side, what are the examples with the smallest margin? There are these two. Okay? And this line that I drew here is actually the line with the highest margin. So what the SVM is going to do is solve an optimization problem that returns this frontier and not this one. Notice that the problem with this one is that the margin of the examples here is very low. Right? Some of the examples are really close. Now, imagine that, the plane here is a minefield, right? And the examples are mines. And your job is to, walk in a straight line across the minefield, right? Would you really pick this line? Heck no. Right? A little stumble and you step on the mine, right? You want to stay as far away from the mines as you can. Okay? So this is what we're going to do. We're going to find the hyperplane with the maximum margin. And by the way, I'm not going to tell you how the theoretical VC dimension guarantees come along, but here's an intuition. I mean, we'll have a little bit more to say about it, later. But here's an intuition that I think is very good. Is that, in a way, so what I do when I maximize the margin is that instead of putting a very thin plane between the examples, I put a thick mattress. Right? This is like a very thick thing that I'm putting between the examples. Okay? Like the thin thing, I could have put it in many different ways. The thicker it is, the less leeway I have to move it around. Therefore, guess what? The lower the VC dimension is going to be. This really, the intuition is just this. We're going to have, so the basic theorem, not to give too much away, right? No spoiler alert here. The basic theorem is going to say that the larger the margin, the lower the VC dimension. And that's why maximizing the margin, intuitively seems like a good idea, but the theoretical reason is that, like, by maximizing the margin, I actually optimize my generalization guarantees. But the intuition is this, is that, like, a hyperplane with a large margin is like fitting a very thick slab of wood. And the thicker it is, the less, room for maneuver I have, the less likely I am to overfit. Okay? Okay, but now how do we actually do this? Right? So yes, we want to maximize the margin. So, let's define the problem. So my margin, right, I'm interested in maximizing the minimum margin, right? The margins of these examples, they're high, and I'm not worried about them, right? It's the examples with the minimum margin that are actually going to be the support factors, because they're the ones that if I move them, the frontier would move. Like, for example, if I take this example, right, and I move it over there, right, guess what happens to the max margin hyperplane? It also slides in that direction because now it has more room. And it still wants to be as far away as possible from these guys. Okay? So how do we do this? Well, first of all, definition of margin. So the margin of the SVM that we're going to try to optimize is the minimum over all the examples of the class. Remember, the class is plus or minus 1 times the weight vector times xi. Okay? This should all be intuitive. The reason I'm multiplying by the... So, remember, this discriminant function is going to be positive, right? Right? When I have a positive class, or should be, right? But what I want, right, is that I want this function and the y to have the same sign. Because that's when I'm making the right decision, right? If they have opposite signs, then the class was plus 1, and this my weight times dot product weight dot product feature vector is going to be negative, right? So I want them to have the same sign, which means like I want their product to be positive. Okay, so I want either y to be negative. Oops, sorry. I want either y to be negative, and this is often called the discriminant function, right? In this case, it's just the weight, it's just the dot product. But I want the class times the discriminant function to be positive, right? So they're either both 1 or both minus 1. You agree? And then in addition, right, I want the margin to be as large as possible, right? So I want this to be as large as possible because the larger it is, the more I am on the right side of the frontier. If it was 0, where would I be? Right on the frontier. Right? So the frontier is where this is 0. Everybody agree? So on one side it's negative, on the other side it's positive. I want to remember, the predicted class is just going to be the sign of the discriminant function. So I want the sign of the discriminant function to be the sign of the class, right? I guarantee that by taking the product, right? They're either both positive or both negative. And then in addition, I want this to be as large as possible. Right? So by the way, there's more than one initial margin. What we're talking about here was always called the geometric margin, and this is now called the algebraic margin. But because the reasons for it are algebraic, and the two are not exactly the same. But let's not worry about those details. Here's, however, something that we do need to worry about, right? Which maybe you are already worrying about, which is, hey, if this is my margin, and remember it's the minimum of all examples of this expression. Well, what's an easy way to maximize my margin? Really easy. And not very smart.
Take the wrong support vectors.
No. Well, I mean, think about it for one particular vector, for all the vectors at the same time. Let's suppose that I already have things on the right side, right? But now the things are, I don't just want to be on the right side, I want to be far on the right side, right? What is a very easy way to make this? Actually, let me ask this another way. What is an easy way to make, remember, what I can vary is the weights, right? What is an easy way to make this function very large? In fact, I can make the margin be infinite just by doing what? By making the weights large, right? Right. The way I've defined this so far, I can maximize the margin by making the weights larger and larger. But that didn't accomplish anything, right? So we need some additional thing here. What is, right? Otherwise, we're not going to solve the problem. Well, what we're going to do is the opposite. And again, this is something that often confuses people no end. And it's understandable why. Is that SVMs are all about maximizing the margin, but then when you look at the actual optimization problem, it's not maximizing the margin. What it's actually doing is it's fixing the margin and minimizing the weights. So if I keep my weights constant, if I say, well, the norm of my weight vector has to be blah, then it makes sense to maximize the margin, right? I can keep the norm of the weight vector. In order to prevent this, right, one thing I could say, like, no, the weights have a maximum norm, right? The norm of the weight vector, has to be less than something, okay? And then I can't cheat anymore. But as it turns out, it's much more convenient to turn this around and solve an equivalent problem is to say, like, no, I'm going to arbitrarily say that the margin has to be at least 1. And then what I'm going to do is I'm going to minimize the norm of the weight vector, which is the dot of the weight product of the weight vector with itself. You see where this accomplishes the same? If the margin is fixed and I keep shrinking the weights, in effect, I'm actually increasing the margin, right? Everybody got this? So here's the problem that we're actually going to solve. The problem that we're going to solve, this is what all SVM learning is about, is this little constraint optimization problem. I want to minimize the norm of the weight vector, And hey, minimizing the norm of the weight vector by itself is very easy, right? What do? If I just said, minimize the norm of the weight vector, what is the optimal solution?
0.
All zeros, right? I can make the weight vectors again. That's not a solution. But this is where the constrained optimization comes in. I want to minimize the norm of the weight vector subject to the margin of every example being at least 1. The margin as I defined it before. But again, notice what's happening here. I don't just want yi and the discriminant function to have the same sign, right? Which means this would only have to be greater than 0. I want to be greater than 1. This is where I'm requiring that I not only be on the right side of the frontier, but be on the right side by this width of 1. And the 1 is arbitrary, right? The reason this works is that I'm going to minimize the weight vector, while keeping this margin, fixed to 1. Okay? Questions?
Why 1 though? Because isn't that going to be constraining the problem?
1 is completely arbitrary. If you don't like 1, pick your favorite number. You want to make it 7, go to town.
I mean,
It's like, why the probability sum to 1, right? Because we decided that, we got to pick a number, so we picked 1. It's the simplest number there is, after all. So, was that your question?
My question more was, is it something that we can tweak, like a hyperparameter, or no?
No, because there is no point in tweaking it, right? Because again, the real point here is that I'm maximizing the margin, right? So, what I'm gonna let me put it this way, right? What I want to do is actually minimize the number of the weight vectors subject to these constraints. Okay? And what you're saying is like, well, what if I made those constraints function, different, right? Is this something that I want to play with? And what I'm saying is that actually you're not going to get anything by playing with that. I mean, you can, but yeah. There will be things to play with. And again, the really important case is when you're dealing with noise, and then we'll see how we deal with using Slack variables. And I think at this point, this whole thing will kind of come together. But I mean, when Vatnik first published SVMs, they couldn't deal with noise and nobody cared. It was finally when they had a version that dealt with noise that things got very interesting. So there were these steps. Maximizing the margin came first, and then came kernels, and then came Slack variables, and then boom. That's when the explosion happened. Okay. All right, so we have to solve this problem. So how do we solve it? We use our extensive knowledge of constrained optimization, right? How many people here have extensive knowledge of constrained optimization? Okay, good. Anticipating that might be the case for some of us, I have here a 1-slide constrained optimization 101. Right? This is why this class is so fun and useful, is that you don't just learn machine learning, you learn all sorts of other stuff like information theory and calculus, and now constrained optimization. And I mean, I'm saying this somewhat facetiously, but really, constrained optimization has all sorts of applications in the world other than support vector machines. Right? In particular, the most famous example of constrained optimization is linear programming, right? Which is, is that ever used for all sorts of things? Okay, so let's see what the problem is and how we solve it. And again, I'm not going to go into the details here. Actually, they don't even matter for what we're going to do here. And at the end of the day, for a lot of the way that the actual learning algorithms work. But it's very important to understand what is going on here. And again, people who just treat SVM as a black box are at a big disadvantage. So let me state so this is a particular constrained optimization problem. Let me state the general problem. And notice that this is a constrained optimization problem with inequality constraints. The simpler version, and the one that is most widely studied and older, is with equality constraints. Okay, so let's first, I don't know if it's widely studied, but it's the simpler one. So let's see what, first of all, the constrained optimization problem with equality constraints is, and then look at the case that most interests us, which is with inequality constraints. So this is going to be a stepping stone to that, but it's also very useful in its own right. So the constrained optimization problem with equality constraints is, I want to minimize f of w. Right, so I want to find the value of w, where w is a vector, that minimizes f subject to a bunch of constraints of the form hi of w is equal to 0. Right, this is just saying that some function of the weights or a set of functions have to have particular values. But when I say function equal to value, I can just put the value on the other side and leave a 0 on the right side, which keeps things more uniform. Okay? So this is the general constrained optimization problem. Okay? And what is the intuition behind this? It's very simple. So unconstrained optimization, with which you're already very familiar, like gradient descent and whatnot, is getting to the top of the mountain. That's all it is. Like, I want you to go to the top of the mountain. That's unconstrained optimization, right? Constrained optimization is, I want you to get as close to the top of the mountain as you can while staying on the road. This is a realistic problem, right? You know, you don't want to get off the road because you might never get back, right? So you're not necessarily allowed to go to the top. If the road runs right to the top, then sure, you go to the top. And then the solution to the constrained and unconstrained problems are the same. But more generally, what happens is that the road zigzags up the mountain and then back down, right? And there's some point at which the road is the closest it will ever be to the top of the mountain. And that's what you want to find. So here, in that case, in this example, what you're trying to maximize, actually not, what you're trying to minimize is minus the height that you reach. Okay? You're trying to maximize the height that you go to. And the constraint is that your position, right, has to be on that curve, the curve being the road. Okay? So far, so good. Okay, now think about it. If this is the problem that we're trying to solve, what defines the solution? What defines the solution so far is like you're in your car, right? You're driving up the mountain, right? When do you know that you have reached the highest point that you can? It's when the path to the top is perpendicular to the road. This, unfortunately, is a very simple intuition that people never seem to give when they talk about constrained optimization. It's very simple. Like, if at any point the path to the top is not perpendicular to the road, then by continuing along the road, you're getting closer to the top. Right? It's only when, in order to get higher, you would have to go at right angles to the road that you can't anymore. Right? If the direction, if this is the direction of the road, like, you know, down the aisle here, right? If this is the road and the top is over there, right? Then I can get closer to the top by driving along the road. I'm not going straight to the top, but when I'm over there, I'm actually going to be closer to the top. I'm going to be higher up, right, than I would be here, right?
So the road's always going up, right? So the road's always going up.
No, it will then go down. No,
but it doesn't dip down and up as it goes.
It can, actually it can. But let's take a simpler case, right? Okay. But it can, actually. This applies just as well in that case. I haven't said anything about the shape of the function or the mountain or the road, right? But whether or not it goes up and down, this will always be true, right? You could get stuck in local optima, but never mind that right now, right? We're not worrying about an algorithm. We're just worrying about, like, what are the properties of the solution. I know that I'm at my constraint optimum if the path to the top is not right angles to the road, meaning there is no way to get closer to the top other than by going off the road, which I'm not allowed to do. Okay? Everybody happy with this intuition? Okay. You know, another example is like, let's say, you know, you're sitting in your room and I tell you, get as close as possible as you can to the North Pole. That's a perfectly well-defined question, right? So what do? Right? The middle of the room is probably not the solution. What you're going to do is you're going to walk until you bump into a wall. The wall that sits between you and the North Pole. Unless, of course, you're Santa Claus and your room is right over the North Pole, and then, you know, then the constraint and the constraint optimization problem are the same. And you know, you can instead worry about the traveling salesman problem or something. Santa Claus has a serious traveling salesman problem to solve. Right? That's a big instance. Yeah. Anyway, so here's a more formal you know, version of this intuition. What am I building up to? I'm building up to this notion of the Lagrangian function and Lagrange multipliers. This was a brilliant idea, you know, that came out of the mind of this famous 18th century mathematician called Joseph Louis Lagrange. Solving a constraint optimization problem directly can be incredibly hard. So first of all, you can't use gradient descent, right? Because, you know, there's no guarantee that when you follow the gradient, you won't violate the constraints. So now you have to try to be optimizing while satisfying the constraints. This could get very hairy very quickly. But Lagrange had an amazing idea. He actually figured out how to turn the constraint optimization problem back into an unconstrained one. And then you just solve the unconstrained one. You know, this is pretty beautiful theoretically and sigh-inducing, you know, from an engineering point of view, sigh of relief from an engineering point of view. So how did he do that? Well, here's the idea. Any solution to the problem must lie in the, so let's call W star the optimal solution, right? This is the solution to the constraint optimization problem. Okay, W star. Star is usually used as a notation for the optimum. Now in an unconstrained optimization problem, at the optimum, the gradient of the function, here it is what? Zero. Right? In unconstrained think back to neural networks, right? The solution of the unconstrained optimization problem is where the gradient is zero. Right? That's what defines a maximum, is that the gradient is zero. Everybody agree? But here it's going to be slightly different. Right? Because again, if I've, the gradient is not zero when I've reached the highest point in the road. It usually won't be. Okay? So what is the defining property? Is that the gradient has to lie in the subspace spanned by the gradients of the constraint functions. I know this is a mouthful, but this is the key idea. Why is that the case? Because remember, the constraint surface is a surface where the function is constant. Namely, it's constantly equal to zero, by definition. And so if the function is constant, then the gradient must be orthogonal to it. Right? Because the function can be changing along a curve where it's constant. Right? So the gradient and the function are actually orthogonal. So the solution, and remember the intuition that we had about the road and the car, right? At your constrained optimum, what it means is that you would have to go perpendicular to your constraint surface, which means that your direction of the gradient has to be only in the directions of the gradients of the constraint functions, meaning perpendicular to the constraint surfaces. Okay? So far, so good? Okay, so now we're almost there. So if this is the case, right, this means that the gradient of the function is a linear combination of the gradients, the gradient of the function, right, is a linear combination of the gradients of the constraint functions. Okay? And another way to say the same thing is to say, I'm going to define a new function, the famous Lagrangian function, that is, denoted by L, that is just the function plus a linear combination. There's the objective function, right, is often called the objective function. It's the objective function plus a linear combination of the constraint functions. Why is this? Because at the optimum, the gradient of this is the gradient of this plus this. It'll be zero, meaning this will be equal to minus this, meaning this will be a linear combination of these as required. Okay? So, here's the recipe, right? And truth in advertising, a lot of people, right, when they study engineering and whatnot, they just remember the recipe and forget the rest. Because the recipe is easy to apply. The recipe is like this. You have, but before we go into the recipe, does this make sense for everybody? You will actually seldom see this intuition for constraint optimization in the textbooks. I don't know why. You'll see a lot of math, but no intuition.
So h of I, W is 0 when you have W star, right?
Yes. Yes.
So will delta of h I W star also be 0? Or it's going to be perpendicular?
No, the gradient is perpendicular, right? I mean, think of a mountain. Right? We're talking about the lines of constant height.
Right.
Right? This is something you see on maps. Right? It's it's the ISO. What do you call them?
Contour lines.
Yeah, it's the contour lines. Yeah, that's a non-technical name, right? The gradient along a mountain is not parallel to the contour lines; it's perpendicular, and that's exactly what's involved here, right? This line is a contour line. It's the contour line where the value is 0. There's a contour line where this is 1, a contour line where it's 2, but this is the one where it's 0. And yes, absolutely, the gradient is perpendicular to that contour line, or it wouldn't be a contour line. Right? If the gradient was not perpendicular to the contour line, then the height wouldn't be constant. Okay? So the recipe is, if you have an objective function f, and you have constraint functions hi, what you do is you form this new function called the Lagrangian, that is the objective function, plus a weighted sum, right, from the linear combination of the constraint functions, and the betas are the weights. Sometimes people use lambdas, but we'll see later why we're using betas. Right? So let me just finish this. These betas are called the Lagrange multipliers because they multiply the constraint functions. And now, so a very simple recipe, right? Going from here to here is a push button thing. And now what you do is you just solve this problem. You solve the unconstrained optimization problem for the new function, for the Lagrangian function. I'm just going to look for the point where the gradient of the Lagrangian is going to be 0. Notice that the Lagrangian function now has two sets of arguments. It has the original so-called primal arguments, the weights themselves, but it also has these interesting new arguments which are the betas, which are the dual arguments, and those are called the Lagrange multipliers. Somebody had a question?
Yeah, we didn't use the fact that it's zero, only that it's constant, like the subject to, like we only use the fact that it's constant, but not that it's zero, right?
No, but that's, yeah, but remember, that doesn't matter because actually equating this to zero is just a matter of convention, right? It could be equal to whatever you want, right?
Yeah, but it's just, where does it come into play? Like, it seems like...
It's, remember, what we saw is that it must lie in the subspace spanned by the grains. You agree with that, right? Well, then all I'm doing is like, write this condition mathematic where it says like the gradient of the function is a linear combination with beta being the weights, right, of the constraint functions, right? Well, if I instead start with this function and differentiate it and take the gradient, I get that expression. Therefore, the two are equivalent. Okay, it's a little bit backwards, and again, you know, Lagrange was a genius for some reason. You know, there's a reason he was a genius, and the rest of us aren't. Yeah.
So is the intuition like between F and H, there are like push and pull forces, and at the point of orthogonality, the gradient just cancels out for each of them.
It's
and hence
not quite. I sympathize with the intuition, but remember, F and H play different roles. Because F, in some sense, is a soft constraint, whereas H is a hard constraint. You are a prisoner in your room. You are not allowed to get out of it. You can walk within the room to try and get closer to the North Pole, but that wall is a wall. So in a way, a hard constraint is like having a constraint with the weight of infinity. Meaning if you violate it, you know, even by a little bit, you're immediately, you know, worse than anything else. Okay, so you know, this is a hard constraint. A function that you want to maximize is often thought of as a soft constraint. Like you want to make it high, but you're not forced to make it any particular value. Okay. Okay, very good. So now, here's how this you know, plays into SVMs. So the way this is often solved, although this is actually not how we're going to do this, but it's how you would do this if you were, you know, if you were in constraint optimization class, is one way to solve this problem is to first eliminate, right? This is a set of equations now, right? Could even be linear equations in a simple case. So you have a set of linear equations in the W and beta variables. One way to solve this equation is to eliminate the betas, which is why they're sometimes called the silent multipliers, because, you know, they're just silent variables. And then you solve, you know, then what you have is a new problem in the original variables W. That's often called the primal problem, because the problem that you started with. But another way to solve this, which often is the one that works best, and it's the one that's going to be relevant to us here, is actually you do the opposite. You actually eliminate the W's and you end up with a problem with only the betas. You have an optimization problem over just the betas. And this is called the dual problem. Right? Because in some sense it's like it's a mirror image of the first problem. At the end of the day, I'm still solving the same problem, it's over a different set of variables. Okay? So what does this mean for all, and those of you who have familiarity with optimization, you know that everybody's always talking about primal, dual, primal, and, you know, this is where that whole, you know, notion comes from. So what does this mean for SVMs? For SVMs, it actually has a really interesting intuitive meaning, which is the following. The primal problem is over the feature weights, and the dual problem is over the instance weights. Right? Remember, the primal problem is, you know, it's a perceptron. I have weights on the features. It may be a perceptron in a derived space, but it's still a perceptron. Okay? So that's my primal problem. The dual problem is the weights are on the instances. And it's actually going to be much more interesting and actually even intuitive for us, because in the dual, what we're doing is we're finding weights for the examples. And if we play our cards right, we will end up with a weight of 0 for most of the examples, which will have enormous computational benefits. Okay? And in fact, the support vector machine, the support vectors in the support vector machine are going to be precisely the weights, the instances that wind up with a non-zero weight when you solve the dual. Okay? And, you know, there are both primal and dual solution methods for SVMs. We're just going to look at the most basic algorithms here. But first, it's good to understand what is the problem that we're solving and how we're solving it. Questions so far? Okay, very good. So, here's the thing. None of this is the real SVM problem yet, because this is the problem for equality constraints. Okay? But remember, what the SVM has is inequality constraints. In fact, it turns out the theory of inequality constraints is much more difficult and it's actually a 20th century, you know, it's a mid-20th century development. So there were 200 years the English people knew how to solve, constrained optimization problems with equality, constraints using the method of Lagrange multipliers, but nobody knew how to do things with inequalities. And then came the KKT theory. Very important thing in support vector machine land is KKT, where KKT are the initials of Karush, Kuhn, and Tucker. So there's this thing called the Kuhn-Tucker theorem, and then there's Karush, actually turned into a solution. So let's see what this is, nomenclature aside. So here's the problem with inequality constraints. I want to minimize an objective function as before, subject to two sets of constraints. The equality ones, which are still the h's, but now I'm going to have a set of inequality ones, which are the g's. And by convention, I'm going to require that the g's be less than 0. So linear program is actually an instance of this, right? Where the function that I'm minimizing is linear. Remember, in an SVM, the function that I'm minimizing, if this was a linear programming problem, we could use a linear programming, at this point, we could use a linear programming solver to learn SVMs. But this is actually what is called a quadratic programming problem, because the function that we're trying to optimize, remember, is quadratic. It's the norm of the weight vector. And in fact, the first thing that people did when they designed SVM is to use a quadratic programming solver, which turns out to be hideously inefficient for these high dimension, many example machine learning problems. But you could use it, a black box quadratic optimizer for this. Okay, and now of course in an SVM, these constraints actually do not exist. I don't have any equality constraints. I just have the inequality margin constraints. But let's again look at the general case. Okay, so now I'm going to have two sets of Lagrange multipliers: the betas for the h's and the alphas for the g's. Right. This is why we picked betas, because at the end of the day, what we want is the alphas. So there you go. And now the famous KKT conditions are what defines the solution. Right? And what are the KKT conditions? Actually, the name sounds very, fancy, but it's just the following. The first one is exactly what you'd expect. That the gradient of the Lagrange and that the solution has to be 0. Same as before. Okay? And then there are these two that really just, the convention, like by convention, like the alpha i's are greater than 0, and the functions, the g's are less than 0. I could have just as easily have picked the opposite convention. Okay? But finally, here is the really important one in general and for learning SVMs. It's what is called the complementarity condition. The complementarity condition. The complementarity condition actually says the following. Let's first see what it is, and then we'll see the intuition. It's a very important intuition. It says that alpha at the optimum, right? So this is what defines the constraint optimum. At the optimum, for each constraint, the alpha of the constraint times the constraint function has to be 0. And what this means is that one of them has to be 0. Right? The only way to make this 0 is to make one of them 0, or at least one of them. And what does it mean for them to be 0? Well, the function, notice, let's look at first at the case where it's the constraint function that is 0. This actually means that the inequality constraint has become an equality one. Right? Right, right, remember the constraint was that g had to be less than or equal to 0, right? When the constraint is 0, this actually has become g equals 0, g of w equals 0, which means, this is now an equality constraint. Okay? And this makes a lot of sense. It means that you were trying to walk towards the North Pole and you bumped into the wall. These are often called the active constraints. Actually, I don't want to draw your attention to that yet, because that's a spoiler. So we say that a constraint is active if its function is equal to 0. A constraint being active means that it has become an equality constraint, because it is the constraint that is preventing you from getting closer to the optimum. As you're in your room trying to get closer to the North Pole, one of the walls will be active and the others will be inactive. Or if your room is pointing exactly northwest, there'll be a corner and two constraints will be active, but most of them will be inactive. Okay? So one of two things is going to happen. Either the constraint is active, or its multiplier is 0, meaning it doesn't matter. So the beauty of this is, at the end of the day, your inequality problem reduces back to an equality one, because each constraint is either an equality constraint again, or it disappears. So after all this complication, we reduced this whole thing all the way back to just doing plain and constrained optimization. It took a lot of smart mathematicians to get there, but we're reaping the benefits now. And now in the case of SVMs, guess what? Guess what an active constraint is? An active constraint is a support vector. The support vectors are the active constraints. They're the ones that have to be there. Like, now it's no longer you trying to get to the North Pole. It's the frontier trying to move around in order to maximize the margin, right? In order to minimize the weight vector, right? The active constraints are the vectors, the samples that you bump into when you're trying to do this. They're the ones that are preventing the frontier from moving somewhere else. But most of them hopefully will be inactive, right? It'll be all the examples that, hey, I don't care where you are. I don't care if you disappear. The frontier isn't going to change. This guy's inactive, meaning its alpha is 0. This guy's alpha is 0, this guy's alpha is 0. This is an active constraint, this is an active constraint, and this is an active constraint. Okay? So when we find our solution, we will have at the solution, in general, in a constraint optimization problem, some active constraints, which means that in an SVM, we will have some support vectors. And the other ones will be inactive, meaning you can throw them away and never remember them or compare with them and save memory and time that way. Okay? So this is the general idea. What we haven't seen is how to actually, before we do that, questions about all this? So, let me clear this. Any questions?
Could we revisit the intuition behind minimization of the norm of the weight vector leading to maximization of the margin?
Yeah, because remember, it's easy to maximize the margin just by letting the weights go to infinity, right? As we defined it. We don't want to do that. One way to avoid it is to say but there's a maximum value that the weight norm of the weight vector can have. Okay. Which means I'm going to say my weights can only live inside a ball, okay. Right? I could have solved it that way. But it turns out to me more convenient to say no, instead of maximizing the margin while keeping the norm of the weight vector, what I'm going to do, it's completely equivalent, is I'm going to fix the margin to an arbitrary value of 1, and I'm going to minimize the weight vector. Okay. In some sense, what I want is I want the margin to be large in relation to the weights. Yeah. Right? Because in increasing the weights is I want to maximize my margin of safety to the landmines. I'm just going to increase the size of everything by 2. Right? Now your feet are twice as big. Yeah. Now the mines are twice as big. Yeah, the margin is twice what it used to be, but you're not any safer. You're still in the same danger of stepping on the mine. Yeah. Okay?
And you're going to go to 4, 6, and it's still going to be the same case.
Yeah, and again, it's going to be easier. It's going to be more convenient for us to minimize the norm of the weight vector because that's the main object that we're playing with while keeping the margin constant rather than doing the opposite. So at the end of the day, we're solving the letter problem because the math is going to be easier. Right? But unfortunately, also introduce kind of this cognitive distance, what happened to the margin that we're supposed to be maximizing. Okay? But really, what we are doing is indirectly maximizing the margin. Okay? More questions?
Can you also revisit the value of margin, where it's yi multiplied by that, by weight?
Yeah, because, so you can think of it geometrically, right, which is usually, where the intuition comes from, but think of it just algebraically, right? What I want is my discriminant function to have the same sign as the class. If the class is +1, I want my discriminative function to be positive, right? Because remember, my class prediction is just the sign of the discriminant function. If the dot product of the weight vector and the example is greater than 0, I predict +1, otherwise I predict -1. What I want is them to either both be +1 or both be -1. Because that means I'm making the correct classification. Okay? But just requiring that doesn't, the margin could be 0. I could be infinitesimally on the right side of the frontier. Right? So what I want is think about it this way. Here's my discriminant function, right? And as I vary my weights, the discriminant function varies. Okay? And I want the discriminant function to, times the class to get bigger than 0, right? We just saw that. But what I don't want to do is I don't want to just stop at 0. Because then I'm in big danger of getting on the wrong side. I want it to be above 0 as much as possible. Right? Suppose that I'm classifying a positive example. Right? The true example is positive. Therefore, what I want is my discriminant function to just be as large as possible. The bigger, the example in the example's class value is 1, but I would rather have the discriminant function be 1,000,000 than it be 0.01. Because if it's pointer 1, it's just a sliver away from being negative, at which point I have the wrong class. Right? So this is the algebraic intuition rather than the geometric one. Right? So I just want to make that function as large as I can. But now I could make it large by making the weights large, and now we get back to the previous point. Okay. More questions? Okay, so now, as I said, we don't actually solve this by Lagrange multipliers, right? Lagrange multipliers are a good way to solve paper and pencil problems, as you will do in concerned optimization class, or for simple problems in the place where a lot of people first encounter concerned optimization is actually in physics, in mechanics. Right? And there you can solve these nice problems by hand. We don't do that because we have computers. We also don't use an off-the-shelf quadratic optimizer because it's too inefficient. So what do we use? Well, there's a whole plethora of algorithms, but the best known one is actually something called, certainly not one of the most usual, but this was sort of like the first real native SVM learning algorithm. It's called Sequential Minimal Optimization, or SMO. And this was invented by John Platt, who was then a researcher at Microsoft Research and is now at Google. So how does sequential minimum optimization work? Again, I'm not going to give you the details, and again, we're not going to ask you to implement this, we're just going to ask you to use an existing package. But let me give you the basic idea, which again is not that difficult. The simplest possible way to solve a problem like this, even simpler than gradient descent, is just update one weight at a time to improve the value of your objective function. Right? Well, let me change the value of this weight to try to make the norm of the weight vector smaller. Right? Easy thing. Right? But the problem is that if you do this, you're going to violate, in general, you might violate constraints, right? Because you're solving a constrained optimization problem. You're not free to just vary examples any old way that you want. So what happens is that, when you tweak the weight of one example to improve the objective function, you have to tweak something else in order to make up for that, such that you stay on the constrained surface. And the smallest number of other weights that you have to tweak is 1. And this is actually what the sequential minimum optimization algorithm does. It's really, really the simplest thing you could do is I'm going to pick an example to tweak the weight. I'm going to pick another example and tweak the two weights at the same time, such that I minimize, just varying, keeping the other weights constant, I minimize my objective function while staying within the constraints. And it turns out for two weights, this can actually be solved in closed form. So what SMO is doing is solving a series of these closed form problems over pairs of examples, where after each step I know that my objective function got better, but because of this trick of using one weight to compensate for the other, I know that I have stayed within the constraints. Okay. And again, there are many details here, and you can find the code in the textbooks, but this is the basic idea of SMO. Okay. And it really took SMO for SVMs to take off as kind of like a realistic machine learning method.
Do I have to pick just one example to compensate, or am I in this?
No, you could pick more, right? I mean, you could optimize all the examples at the same time, but the simplest thing that you could do is optimize just one more. It can't be one because you would violate the constraints. If you're now bumping against the constraints, right, and you change one weight, obviously it's like you just drove off the road, right? The smallest number I can pick is one more, and now it's very convenient because I don't want to, the thing that's good about just picking two is that I can solve it in closed form. So I can just do a series of, the analog of the sequence of gradient steps in gradient descent is solving a sequence of these problems. So each one of them had better be very cheap. Imagine if this problem was itself a big optimization problem, this would be very slow. Okay? And this problem in general will not, this algorithm in general will not work very well for arbitrary concerned optimization problems. It works well for SVMs because the problem tends to be very sparse. Because it's sparse, the generic quadratic programming systems are very inefficient, but also this one, it actually works very well. Okay? Because you don't have, if it was the case that with these very big complicated interactions between lots of things all at the same time and all of the support vectors were relevant and whatnot, then this would start to become difficult. But in general, that's not the case. Again, what this process is going to do is it's going to drive, hopefully, most of the weights to 0. Right? I mean, again, if you look back to this figure, right, what should happen is that most of the weights go to 0 because the examples are not defining the frontier. So the result is going to be very sparse in the sense that only a few of the constraints will be active. So really, even though there's a lot of constraints, right? Every example has a constraint. The ones that you really need to worry about are usually a fraction of all of those. More questions? Okay, very good. So finally, or not finally, so now let's see how we handle noisy data. And then let's see why, what are the theoretical guarantees that I've been talking about, right? And, that would actually be short, but I think it kind of like completes this whole package of learning theory and support vector machines. So the problem with everything that we've seen so far is the same as the problem with the perceptron algorithm, is that like, you throw in one noisy example and this thing crashes. Right? You can see why, right? Look at this figure, right? If this example is not positive, there is no hyperplane. I know that with kernels, right, I can create a curve, but like the curve is going to do something like it's going to go over there, and I mean this is going to be a complete overfitting catastrophe. Okay, so even though I can, once I use kernels, I can have a line that correctly classifies all the examples. I don't want to do that because that's the thing to be overfitting up the wazoo. Okay, so what can I do? Well, of course, the whole problem is that this is machine learning. It's not optimization. I don't actually want to fit this example. I want to ignore it because it's noisy. Just as with, remember decision trees? I want to ignore the night when, she was, she had the headache because she had a hangover from partying the night before, and then want to play tennis. Same thing here, right? This is the night, this is the headache Saturday morning. We just want to ignore it. At the same time, we're not free to just ignore things at our will. There has to be a price that we pay for ignoring things. So here's the idea, and again, it uses a very common notion in constraint optimization, which is the notion of slack variables. Although to be fair, the way slack variable used here is very if you remember linear programming, in some ways the best thing you can do is forget that you've ever heard of slack variables because the use here is going to be different. So again, it's a little bit confusing, but if you never heard of slack variables, then good, you don't have to worry about that. So here's what we're going to do. We're going to introduce a slack variable. For each example I, I'm going to introduce a slack variable xi I. So this is the Greek letter xi. Right? We've already used alpha and beta, and now comes xi. Okay? And now what I'm going to do is I'm going to change my constraint optimization problem to the following. I want to minimize the norm of the weight vector plus the sum of the slack variables. And what are the slack variables? Is that I'm no longer going to require that everybody have a margin of 1. I'm going to allow it to be a margin of 1 minus the slack. So something can be on the wrong side of the frontier. It can even be on the wrong side of the frontier by a lot. But the more it's on the wrong side of the frontier, the bigger the price that I pay. So I'm trying to minimize the sum of the slack variables. And by the way, you see this C here? It's too much. She can't take the slack. you see, we're just slacking off too much here. You see the C here? This is actually the key control parameter in the SVM. Every good learning algorithm has a bias variance trade-off parameter, and it's right here, because this is what's trading minimizing the norm of the weight vector against basically slacking too much, allowing a lot of examples on the wrong side of the frontier. And the way you usually set this C is by cross-validation, right? Right, I'm just telling you all the important answers in machine learning, right? Overfitting, XOR, nothing, cross-validation is another very important one, okay? So usually set these guys by cross-validation, okay? And now notice, this is just another constraint optimization problem. We can generalize SMO to handle this. Of course, a quadratic programming solver would solve this. It's just a very simple quadratic programming problem, okay? So we're solving a different problem, but now we actually have the ability to handle noise and not collapse or overfit. And it was when this final piece was added that SVMs, shot to glory. Okay? Questions about slack variables and noise in support vector machines?
So what values you assign to psi? Like how is that determined?
No, the psi is a new variable in the optimization.
Okay,
so remember before, right? Let's compare this with the old problem, right? Before, the variables in my optimization were just the weights, right? And then there's going to be the dual variables, the betas. They're still going to be here, but let's not even think about it for just a second. Now, in addition to the weights, I also have the slacks. my optimization is going to be varying the weights and the slacks. I mean, literally, if you think about this geometrically, I'm going to be moving the hyperplane around, as a result of which the slacks for the variables that are on the wrong side are also going to be changing. I am going to try to get, so for example, here what's going to happen, right, is that I'm actually not going to completely ignore this guy. The hyperplane is going to move a little bit closer to it because it's still trying to minimize that slack. But the payoff for minimizing that slack is going to be very bad, right? So actually, in the worst case, it may, or in the best case, it may not even move, right? But in general, it may move because it's trading off trying to reduce the slack with now reducing the margins of the examples that still are within the margin. Okay? So now I'm trying to, remember, moving the hyperplane is changing the weights. So I'm changing the weights, but I'm also, changing the slacks. So both of these are now variables in the optimization. Yeah.
What is psi I mathematically for each?
Sorry?
What is psi I? I mean, the definition of psi I exactly mathematically, like what's it equal to?
The definition of the psi I is this statement here. Right? Pretend for a moment that I didn't tell you anything about slack variables. I said the way we're going to handle noise is that we're going to modify the the optimization problem to be this problem here. Right? Minimize the weight vector, your real variables of interest, plus this C sum of I of psi I. Right? I'm free to write this expression. Right? Subject to the constraint that, blah, blah, blah. This is a valid optimization problem, and it does allow you to handle noise. And now, because we like to give things names, we call these guys the slack variables. Right? So they are defined by the problem. It's not like I define them and then I put them into the problem. I define the problem this way, and then these interesting things, new things that appear in it, I just call them the slack variables. And use letters, psi to represent them. There's nothing deep there. Yeah.
Question?
How they get initialized?
Oh, that's a good question, right? So, for example, actually, let me say something higher level. It doesn't matter. The beauty of a convex optimization problem is that you don't care how you initialize things. You always get the same solution. For efficiency purposes, different initializations might be more useful or not. But usually, at least at the level of interest to here, people actually don't worry about that. You might, for example, just initialize all the weights to 0, and then the slacks will fall out of that, right? Remember, the slacks are a new set of variables, but they're actually variables that are a function of the real variables, which are the position of the hyperplane. So another way to pose your question is like, what should I initially make my hyperplane? Right? What should be my initial weight vector? The short answers could be anything, and then the answer is like, well, if you have something more intelligent than making them all 0, please make them that. But whatever you make, right, whatever the weights are, given the examples, you will get their corresponding slacks, right? Because you've put down the hyperplane, and now the slacks follow from that. Given the hyperplane, some of the examples will be within their margin, and some of the examples won't. Yeah.
I can initialize the betas to 0, right?
Well, if you are solving the dual problem, then you can then the same considerations that we're making about the W's you might apply to the betas. Right? You could say, for example, your suggestion is initialize the betas to 0. Initializing the betas to 0 means I'm ignoring all the constraints, which means I will get a terrible solution, but then my optimization will cause the solution to get better. So again, initializing the betas to 0 is not wrong. It might be inefficient, but you'll still get to the right solution. You actually don't care where you initialize because it's a convex problem. Yeah. Okay, so finally, why is this so good at generalization? I mean, empirically, support vector machines tend to generalize much better than methods that went before. There's also a theoretical reason for that. And the reason for that is that you can actually, and this was the rationale behind the development of support vector machines. It's that what I want to do is I want to have a learner with the lowest possible VC dimension, right? That still fits the data. That's how I get generalization guarantees. And what Vapnik showed is that there is a relationship between the margin and the VC dimension. The higher the margin of the hyperplane, the lower the VC dimension. And again, I'm not going to prove this here. It's actually not that straightforward of a proof. But remember the intuition about the thick slab of wood. Okay? The thicker it is, the less I'm able to jiggle it, and therefore, the less ability I have to overfit. So this is what are called margin bounds. So there's a relationship between the margin and the VC dimension, right? And therefore, right, if I maximize the bounds, I minimize the VC dimension, and I optimize my guarantees. Meaning, I either minimize the amount of data that I need to have to guarantee delta and epsilon in the pack learning, right? They're probably approximately correct, or for the same amount of data, I have a better delta and epsilon. Okay. Now, fortunately, for our intuition, and by the way, let me sort of like hark back to something that we said before. Why is it that some people naively claim that SVM solved the curse of dimensionality? Because the dimensionality doesn't show up in these bounds. Isn't that amazing? So the generalization doesn't depend on the dimension. What is the fallacy in that argument? Is that when you have, guess what? When you have higher dimension, you tend to get lower margins. So the dimension is not being explicitly considered, but implicitly, the curse of dimensionality is still there. Having said that, maximizing the margin delays the onset of the curse of dimensionality compared to just ignoring it. Okay? We can also look at this in the context of a different type of margin of bound, which is actually much easier to understand, and in fact, ironically tighter. As in most pack learning, these bounds tend to be very loose. So whether or not they really, really capture what's going on is something that you could debate. But here's bounds that tend to be tighter. They're the leave one out bounds. And the leave one out bound just says the following. It's an amazingly simple piece of reasoning. It just says that the expected true error of the hypothesis is upper bounded by the fraction of the examples that are support vectors. It's a really easy statement to understand. If only 10% of my examples are support vectors, then my expected error is at most 10%. Meaning that if I have very few support vectors, I have very high confidence that that my learner generalized well. And you know what the reason for that is? It's really simple. It's leave one out cross validation. Any vector that is not a support vector, I can just take it out and nothing changes. The only examples that could cause an error when I take them out are the support vectors. Therefore, the maximum number, let me put it this way. The examples that are support vectors, if I take, let's go back to this figure, right? This example, right, if I do leave one out cross-validation, will be, this is a bad example. It's the noisy one, but never mind, right? So let's take this example, right? This example, if I do leave one out cross-validation, will be correctly classified, right? Because the frontier is still going to be in the same place, and it classifies the example correctly. The only examples that I might get wrong when I take them out are the support vectors. Because when I take them out, the frontier might move, and I might get them wrong. I might still get them right, but the point is, there's an upper bound on the number of examples that I will get wrong in cross-validation, and that's the number of support vectors. Because the ones that aren't support vectors, I'm guaranteed to not get wrong. Because so I have a very simple generalization bound, which is the expected error is just at most the number of support vectors. And in fact, as I said, this bound, even though it's much less popular with the theoreticians, this is actually the more important one, because this is way tighter. This bound in particular is never greater than 1, whereas the margin bounds often what they will say is that, oh, your error is going to be less than 500%. Well, thank you. I already know that it's less than 100%. I mean, this unfortunately can happen because, as you saw, the bounds are pretty loose, right? Remember, there's always that union bound in there that makes things loose. Now, again, you could look at this and go, but hey, doesn't that mean that that SVM solved the curse of dimensionality? I don't see the dimensionality anywhere in here. Well, guess what happens when the dimensionality goes up?
Number of examples.
The number of support vectors goes up. Why does the number of support vectors go up? Because now everybody's near the frontier. So again, it looks like you solved the curse of dimensionality, but you haven't quite. But still, this deals with the killer problem for nearest neighbor is the curse of dimensionality. In the way, what SVMs do is they greatly alleviate that problem. They don't solve it, but they do greatly alleviate it. Okay. More questions? Okay. Amazingly, we're actually slightly early today. We've made very good progress. Next week, we're going to talk about something completely different, unsupervised learning. So I'm not going to start today. You'll actually get to go home early. I have one small piece of bad news, which is, or good news, depending on how you look at it, which is I'm actually going to be out of town next Tuesday. So the class will be taught by guest lecturers. So I won't be here, which means we might not ever see each other again. I hope that's not the case, but either way, I hope you enjoyed the last class. I hope you enjoyed, finishing your projects. And most important, please keep in touch. When you apply this stuff, let us know what happened. I want to know both your successes and failures. Tell us the things that you learned in this class that were good versus the lies that I told you. So I know not to tell them to the next generation of students. And again, hopefully we will bump into each other many more times. Partly because I'm not only an instructor, I'm also the director of the program. But in any case, good luck in your endeavors. All right. Yeah. Good. That's the spirit. Yeah. Question. Oh, okay.
It's a binary, right? Binary?
No. Fair point, right? I think since I'm not going to be here next week, it makes sense to tell the answer now. I'll tell you the answer. I won't tell you how, but I'll leave it for some. This would be like those exercises at the boundary that you have the solution at the back and we don't say the solution. The solution is sine of a over x. And what is the intuition is that sine of a over x, right, is a curve that has many oscillations close to the origin and fewer farther away. Right, sine of ax oscillates